built this desktop CNC mill that can machine metal. A lot of small and big tricks went into making it sturdy and precise. I want to share them all with you in this video, so stick around for those and also to find out how the machine actually performs. There are a lot of desktop CNC machines that can be bought off the shelf, but somehow none of them seem to fit my requirements. I wanted the machine to be small enough to fit on a desk but sturdy enough to machine steel. I wanted it to be precise within plus minus 0.1 millimeters, and of course, I wanted it to be cheap. All of this is extremely demanding. Since I had no off-the-shelf options that would fit these requirements, I decided to design and build my own. My design consists of a base on which the Y-axis rails are mounted. The Y-axis is driven by two stepper motors. To make my life easier, I'm going to use these off-the-shelf linear stages for my X and Z axes. I've used them in the past and I know that they're very sturdy and precise. Now the plan is to make this entire structure out of aluminum, and generally, metals like aluminum have terrible vibration damping. But vibration damping is essential in an application like this. To mitigate that issue, I'm going to use cast aluminum, which is slightly better than cold rolled aluminum, but that in itself isn't going to be enough. So to get further help with vibration damping, I'm going to fill these regions here with epoxy granite. The combination of aluminum and epoxy granite will give the machine the required rigidity and also provide the necessary vibration damping. This finalizes the design. With so many metal plates to cut in many shapes and sizes, I was lucky to have access to a water jet cutter which uses a very high pressure and thin jet of water mixed with grit to cut metal. All the metal plates ready, I started tapping the holes. It felt like I must have tapped a million holes, but finally, I'm ready to start assembling stuff. The first step now is going to be to assemble the base. I will apply silicone on these gaps so that when I pour the epoxy granite, the epoxy will not leak out of these. The base is now ready for the epoxy granite pour, but before that, I need to find the right ratio of sand and epoxy that will form our epoxy granite. To find out the formulation, I mixed a small quantity of sand and epoxy in a ratio of 80:20, 75:25 and 70:30 by weight. As you can see, the 80:20 is too dry. There isn't enough epoxy to wet the sand, and 70:30 is too much epoxy. You can't even see the sand since it is completely drowned in epoxy. So 75:25 seems to be a sweet spot. Now back to the actual build. The epoxy itself is a two-part mixture, so that requires its own mixing and then the mixing of the epoxy with the sand. So in short, a lot of mixing and then pouring. This is where I realized it might have been better to use a finer grit sand to get a better surface. But since none of the epoxy granite surfaces are going to remain exposed, I should be able to live with it. After 48 hours of drying, the base is flipped and ready. Now I need to install the y-axis rails and then align the two rails to make them parallel to each other. Some adjustments and things are looking good. The base is ready. The next is to assemble these pillars. Off camera, I poured epoxy in these pillars. Unfortunately, I saw significant underfilling for these pillars. It would have been better if this wouldn't have happened, but not the worst thing to happen here. I might be able to live with it. I will just cover these up and nobody will know. Following that, the x-axis linear stage is mounted on the pillars. Now I will mount the entire assembly consisting of the pillars and x-axis assembly on the y-axis linear rails. The next step was to attach the ball screws with the pillars and x-axis assembly, but lo and behold, I realized that when I mounted the plates that hold the lead screw, I mounted one of them upside down. So now this plate that is supposed to attach the lead screw to the assembly works fine for one side, but it isn't going to work on the other side for us. I didn't want to go back to the water jet cutter just for this. So for now, I will create a slot in the plate to make it work. Once I have this machine ready, I will use it to machine a metal plate for itself to replace this one. This is what the end result of the fix looks like. The X and Y axis integration is now complete. It's now time to assemble the Z axis linear stage onto the X axis. This Z-axis plate assembly, which will hold the spindle, has epoxy granite filled in it. It will get assembled next onto the Z-axis. The motor mounts for the Y-axis are next to get assembled. This is where I have to issue a do not try this at home warning. As you saw in the earlier part of the video, because I mounted the ball screw plates upside down on one side, one motor mount had to be bolted in from the underside. Trying to hold up the machine with one hand and bolting something on the underside of the machine is not a good idea. I assure you that the broken finger that you may or may not have noticed in the earlier part of the video did not happen because of this, but it just goes on to tell you how careless I am. Next, all the motors get mounted. Mounting the motors and covering the exposed epoxy granite areas, this is what the machine looks like. Next step is to mount the spindle, but before that, we will have to wire it up. Now this video is not a tutorial on how to wire a spindle. The idea here is to show what I did. There are several videos that describe this process in detail. I will put the links to these videos in the description. Please refer to those before you wire a spindle. What I have is a 1.5 kilowatt spindle which I will drive with a variable frequency drive or a VFD. A VFD takes in two-phase electricity from a regular wall outlet and converts it to a three-phase that is needed for the spindle motor. From the wall outlet, the black or the hot wire goes to the R terminal on the VFD, white wire or the neutral wire goes to the T terminal, and then the ground goes to the ground terminal. This color coding is specific to the part of the world you live in. I live in the US, so this is what it was for me. The four wires that go to the spindle get connected to the U, V, W and ground terminals on the VFD, and their other ends get connected to terminals 1, 2, 3 and 4 on this connector that is provided with the spindle. As far as I know, the ordering of the UVW terminals does not matter, but 4 has to be connected to the ground. But please watch the other videos in the description before wiring your own spindle. Let's try this out. No smoke and the spindle is spinning, so that's good. Next step is to mount the spindle. Initially when I designed the machine, I was planning on using a 500 watt spindle. I changed my mind later and switched to a 1.5 kilowatt spindle but forgot to update the position of the mounting holes. So I'm going to have to use a 3D printed bracket to hold the spindle. I know, Not a great idea. This will come back to bite me in the backside later, but for now, I will be able to live with it. With that, the machine assembly is done. Now we can move on to machine alignment. We are going to have to perform two sets of alignments. One set of alignments is to make the travel of the three linear axes perpendicular to each other. And the second set of alignments is to make the spindle axis parallel to the z-axis. Let's jump right into it. First, I will align the x-axis such that it is perpendicular to the y-axis. The setup I have consists of a machinist square that is butted up against the y-axis rail on one side. I'm tramming the square to check the alignment. As you can see, initially the x-axis is not perpendicular to the y-axis. To adjust this, I will rotate the ball screw on one of the motors. This moves only one side of the x-axis, allowing us to adjust the perpendicularity. Now post-adjustment, things are looking good. Mind you, the dial gauge I'm using is very sensitive. Each division on it is 0.0001 inch or about 2 microns for the people using metric units. So right now, we are off by about 2 thou or so over such a large travel. That's not bad at all. Next up, I will have to make the z-axis perpendicular to the xy plane. It is very obvious that we are way off on this. To make the adjustments, I had to shim the z-axis. Post shimming, we are about 2 to 3 thou off over a large z travel. I will be able to live with that. Similar alignment was done by rotating the spindle by 90 degrees. This concludes the alignment of the axes. Now on to the spindle alignment. For that, I 3D printed a tool that holds a dial indicator on one side. It has a hole in the middle for a M6 bolt to pass through it. The bolt is then clamped in the spindle, which allows the tool to be rotated with the spindle. We want the same reading on the dial indicator at the front and the back positions and at the left and right positions. And to align the spindle though, we should only shim or adjust the spindle bracket or the plate that holds the spindle and not any of the linear axes. This is what the result looks like post shimming. Same process was followed to do the left and right positions. The machine is finally ready. Now comes the most exciting part, which is testing. Feeds and speeds for CNC machines are very machine specific. What works for one machine may not necessarily work for some other one. I'm still trying to get to know this machine, but here is how the first few trials went with aluminum. I'm using adaptive clearing tool pads, and we are essentially cutting dry here apart from an initial squirt of lubricant. The optimistic that I am, I started off with very aggressive feeds and speeds of 500 mm per minute and 20,000 RPM. That didn't end well at all. The tool got clogged with aluminum and the workpiece got too hot. I realized that this might be because the high RPM is causing too much friction between the tool and the workpiece. So in effect, it isn't cutting the material but just rubbing against it. So I dropped the RPM to 12,000 and that worked wonders. This is attempt number 2 with the same feeds and speeds and better clamping. first pocket gave a decent surface finish, but when I clamped the workpiece better for the next cut, it gave a very good surface finish. There is some chatter because of the plastic 3D printed spindle mounting bracket I'm using. Remember, I said it will come back to bite me in the backside? Fortunately, that is a temporary problem. But overall, the surface finish is nice and shiny. I call that a win. With that win under my belt, I machined a pocket in aluminum with the same process parameters. This is the end result, nice and shiny. For steel, I'm using a feed of 100 mm per minute and speed of 5000 rpm. I had to periodically clear out the chips with compressed air. It is able to machine steel, but the surface finish isn't great, and again, the root cause seems to be the mounting bracket. Overall, I'm quite happy with how the project turned out. The machine has a ton of potential. There are several improvements that need to be made, first of them being the mounting bracket. I also plan to build an enclosure around this thing and potentially a mist coolant system. But those will have to wait for now. If you liked the video, please help out my up and coming channel by hitting the like and subscribe buttons. See you all in the next video.